Hi there. Welcome back to Core C++ Part 10. I'm Stefan T. Lauid, and today I'll be talking about some of the features that we had added at the end of Visual Studio 2013 RTM, but also a whole bunch of new features that are available in a CDP. So at the end of Visual Studio 2013, we had actually implemented a few bonus features which I had blogged about. If you looked at the Visual C++ team blog, I've got a long post up there called C++ 11.14 STL features, fixes, and breaking changes in VS 2013, where I mentioned all the features that had shipped in the previous CDP. That was back in November 2012. Those shipped in a more polished form in RTM. But we also found the time to sneak in a few more features into the compiler. And I'll be talking about some of those today. Now it's November 2013, and we have a new CDP for you. So the official branding of this thing is the Visual C++ Compiler November 2013 CDP. I would like to, and internally it is being referred to as codename Torino. The previous one was Milan. I think Herb Sutter had chosen that codename. I want to point out a few things about this because the branding is a little confusing. First, it says compiler. So this is a compiler-only preview. They are not updating the CRT and the STL. It's, for setup reasons, is rather hard for them to update that stuff. And in any event, we're just getting started with our library changes. So you will not see any STL changes. We've been working on them, but they won't ship in this CDP. Second, it says November 2013. This is a date. It is not a version number like VC 2013 RTM. You should not expect these new features to ship in update to 2013 RTM. The compiler team may decide to do that, but you should not expect it. I consider it very unlikely. Shipping things in updates to RTM versions requires extensive validation. They need to be really sure they're not going to break anything. And in the past, they have almost never done that. So you should probably not expect to see them in that applied to 2013. However, it is very likely that all of these features will appear in the next major version after 2013 RTM. They have not announced the branding yet. In fact, I don't even know what that branding would be called. The only reason we would pull a feature that has actually been implemented already is if we found like dire bugs in it, or it's always possible for the C++ Standardization Committee, WG21, to decide to vote out a feature, which happened with concepts in C++ 11 during C++ OX's evolution. All of these features, they look pretty solid. I haven't seen any grumbling in the committee about, oh yeah, we should totally pull this out of the core language. Although that did happen to a couple things that aren't on this list. They decided to move arrays of runtime bounds into an array extensions technical specification. And they also moved a couple of library features, dynearray and optional, out of C++ 14 and into a library technical specification. So it's not an iron promise that all these features will appear in the next major version, but that's certainly what we're thinking of. So this CDP, and that's Microsoft speak for Community Technology Preview, or Alpha, which everybody else would say. We're releasing this to show you, hey, here's some features to play with, gain experience with, and also for you to try to use these features in your code base, and most importantly, report any bugs that you find, because now is the time to report bugs. We have plenty of time to fix them for the next major version, especially if you maintain anything like an advanced C++ library like Boost developers. Should totally be downloading this and seeing if all of these features are implemented properly and work with their library. So before I get to all the CDP features, I'll read them all out. I want to go over the features that we shipped in 2013 RTM. And my blog post, which I've got up on the screen here, I was mostly covering STL features and a whole bunch of fixes that we had shipped, but I also mentioned the core language features. Let me give you a test drive at least of alias templates. This one is a really cool feature. It makes the lives of template programmers much easier. So here I'm running 2013 RTM. This is the product that you can install right now, and it's ready for production. The idea behind alias templates is to fix a problem that was in C++ 98. You can have type defs in C++ 98 going all the way back to C, but they can't be templates. So if you wanted to have anything like a templated typedef, C++ did not allow you to do that. There are workarounds for this, like having a templated struct with a nested typedef inside. And those are obnoxious, especially because you have to say type name, ; type all the time. In C++ 11 and in 2013 RTM, there's new syntax called alias templates that make your life easier. So I've got an example here. This example is also showing something else that works in 2013 and in C++ 11. In the STL, they took the STL allocator requirements, which were very verbose. I have a very old blog post going back to like 2008 called the Mallocator, where I showed a C++ 9803 allocator, and they require a whole bunch of nested typedefs like pointer and reference and member functions construct and destroy, and they're almost always boilerplate. In C++ 11, the requirements for allocators were minimized. And what this means is that if you provide a user-defined allocator, like here I've got template typename t struct myalloc, you only have to provide a few fundamental things. And if you don't provide other things, the compiler and the C++ standard library will essentially fill in the blanks. They'll say, oh, wow, you're not defining a difference type. I'm just going to use iterative t. You're not defining a size type. Oh, you must want std size t. So you only have to provide really the most important operations. In 2012, we got most of that working in the STL, but due to a library bug, one thing didn't work. You still had to provide a nested rebind struct. In 2013, we fixed that, so a truly minimal allocator will now compile. So here I've got a myalloc, and I just need to provide a default CDOR, a rebinding constructor, equality, inequality, and then I can get right to the fun part. Here I'm providing an allocate function that's going to go allocate memory from somewhere. This one, just for demonstration, is going to print out a string, proving that it's being invoked. And then it's going to do integer overflow checks. Then it's just going to call malloc. Here I could do something smarter, but malloc is the simplest thing to call. I'll throw bad alloc if I get null, and then I'll return it. Similarly, deallocate will print out a string proving it's being invoked, and then call free from the CRT. So this is a C++ 11 minimal allocator, and I've defined this so I can show you the alias template. After including the vector header, I can say, and here's the new syntax, template on type name t. Using, the C++ Standardization Committee really hates introducing new keywords, so they use the existing keyword, and here it makes sense. You say using and then the name of your alias, and this I'm going to call my vector. And then you put an equal sign, like you're initializing a variable, and you say, OK, my vector of t is equal to a std vector of t and my alloc t. So I can reuse the type name that I defined in the template here, just as I would be able to in defining a template struct. So in main, instead of saying std vector of int myalloc int, I can use my alias template. And I just say my vector of int v, and then I can use C++ 11 initializer lists. And if I compile and run this, it'll build, and we will see that the my vector is allocating and deallocating memory for my custom allocator. In this case, I'm running in debug mode, so it's doing an extra allocation behind the scenes as expected. So that's alias templates. Let me show you just quickly on the whiteboard the other couple of features. Let me stop this here. No, I need to shift F5. There we go. I want to keep all this for a second. We are in a temporary studio right now, so I don't have my usual whiteboard. So the other features that are implemented in 2013 RTM are defaulted and deleted functions. So in a class, if I have something like struct x, okay, I can give it data members. If I want to make x non-copyable, in C++ 9803, you had to do this sort of squirrely dance where you would make a private, unimplemented copy constructor and copy assignment operator. And any attempt to invoke these things would then violate access control, and you would get a compiler error saying, whoa, this thing is private, you don't have rights to it. Or if you are yourself within the class, because you left them unimplemented, you would get a linker error. And it would say, whoa, unable to find definition of this copy constructor. So it did make the things non-copyable, but it resulted in sort of weird compiler errors. In C++ 11, you now have dedicated syntax to be able to say, hey, this thing here's the signature of it. Any attempt to invoke it should trigger a compiler error. So here, if I say, OK, x is going to have a public copy constructor, and I would say constexpr, if I say equals delete, this syntax essentially makes this copy constructor signature a compiler error if you attempt to invoke it, and similarly for the copy assignment operator. Conversely, imagine that I want to make my thing non-copyable, but I would like to have a default constructor. So C++ has a rule going back to C++ 9803 that if you declare any constructors, copy or taking two ints or whatever, the compiler-generated default constructor is inhibited. It's not generated for you. But what if you want it anyways? Well, you can always define one yourself as a user. But in C++ 11, you can also say, give me the default definition. For a default constructor, this is usually not so interesting. But there are special rules now around when a class is considered trivial and plain old data and so forth, where the compiler-generated version actually has special properties. So if you want to request that, here I could say xpren for the default constructor equals default. And this gives you a defaulted definition as if the compiler had generated it for you. However, in 2013 RTM, there's one thing that you can't do, and that's you can't request equals default for a move constructor or a move assignment operator. I refer to this as R value references v3, the rules for implicitly generating move cdors and move assigns. The compiler in 2013 RTM doesn't have the logic to omit a member-wise move. So you don't get them generated automatically, and you can't ask for them with equals default. That's just a limitation, but it's being lifted in the CTP. The other thing you can do in 2013 RTM is what's called non-static data member initializers. That's a mouthful, so everybody usually refers to them by their abbreviation NSDMIs. And this allows you to say, OK, maybe X has a couple integer data members, int A and int B. What if you'd like to say, maybe X has 50 constructors. For every constructor where I don't explicitly initialize A, just give it a default value. Like here, I would like A to be maybe 5, and then B to be 0, or whatever. Now, a constructor with an initializer list can then override this and say, oh, I actually have a different value I want to use for A and B. But if a constructor doesn't specify anything, then you'll get these default values. This is illegal C++ 9803, but permitted in C++ 11. You just say, here's your data member, then you give it an initializer, and that'll be used in every constructor automatically if the constructor itself does not provide another initializer in the member initializer list. These are so simple I didn't even want to write a simple program to show you how they work. So now let's look at the features in the CTP. I actually have snippets prepared for all but the last two that we can look at. So what I'm running here, actually let me close my IDE. What I'm running here is just a command line version of the toolset. I literally built this a couple of hours ago from our current enlistment. What we'll be shipping in the CTP, it'll be an installer, then install the toolset. I believe they're actually going to hook it up to the IDE just like they did for the last year's CTP. But because I don't have that installer right now, I'm just running our command line toolset. You'll be able to also run things from the command line, although you may have to modify your path slightly. Then here I've got my editor. OK, so let's look at the code that I have. OK, so let's look at the features in order. I think everything will be simpler if I show you examples rather than giving you a whole blast of information and then a whole blast of code. So first, I've sort of sorted these by order of popularity, although it's sort of a random order. R value references v3. Finally implemented in VC. So this is sort of my own terminology. What I refer to as R value references v3 means that VC will now follow the C++ 11's rules for automatically generating move constructors and move assignment operators if you don't provide them yourself. There are also rules in C++ 11 where if you declare if you declare a copy constructor, then the compiler says, wow, you're doing something fancy, perhaps allocating a new chunk of memory, copying bits over, or like you're implementing a string or a vector from scratch. If I implicitly generated a move constructor for you, then that would totally corrupt your class. So the presence of a user-provided or user-declared copy constructor, actually I think it's user-provided, sorry, I'm quoting the standard from memory here. The presence of a user-provided copy constructor will inhibit the automatic generation of move constructors and move assignment operators. All of those rules and vice versa, those are part of rv-references v3, and they are implemented in the CTP. Additionally, the restriction about not being able to say equals default to request a member-wise copy construction or member-wise copy assignment, that has been lifted. So in the CTP, you'll be able to say equals default for move CDOR or move assign and get them generated by the compiler. So let's look at this. Here I've got a test program, and here's a simple struct I call noisy. I've actually got my editor on my work computer configured to spit this out when I type a little shortcut. This has simply been instrumented so that attempting to default construct it or copy it or move it or destroy it will print out what's happening. I like this because it shows me what's actually being executed without stepping through the debugger and possibly getting confused. So this is something that I can write in 2013 RTM. But now, if I have a class that contains a noisy data member, so here I'm calling this noisy int, where I have a noisy data member n, and I also throw in a couple extra ints, int I and unsigned long. Here I'm using non-static data member initializers. In 2013 RTM, noisy int would not get an automatically generated move CDOR and move assign. But in the CTP, it will. So here in my test function, if I construct a noisy int called source, and then I construct a destination, and I move construct it from the source, this will invoke the compiler-generated move CDOR for noisy int, and that will then do a member-wise move of all of its data members. And so it'll move the noisy. It'll also move the integer and unsigned long. But those are just plain old data, so they're just going to get bitwise copied. So here, I can show you what will happen if I compile and run this thing. It'll also print out the stuff from the other test cases, but here's the stuff coming from this test case. I get a default constructor from the first source object. Then the construction of dest invokes the move constructor. This is new. VC 2013 RTM would not print this. And then I destroy both source and dest. So awesome. That proves that rv-references v3 works. Let's see, next feature. So as Herb Sutter announced back at the build, I believe it was 2013 conference, the compiler team is trying to achieve full conformance of both C++11 and C++14, and they are picking features in priority order. So this means that some very important C++14 features will be implemented before some less important C++11 features. For example, attributes is Herb's favorite example of a C++11 feature that will probably be leaving later rather than sooner. Here, C++14 has a feature that allows you to get automatically deduced return types for ordinary functions. In 11, lambdas got this feature where you could just say return an expression, and the lambda would get an automatically deduced return type. In C++14, this has been extended and enhanced to also cover plain old functions. So let me scroll down. Okay, so these new return types, like I said, the committee really hates introducing new keywords. They're introduced by the auto keyword. So here I have a template function. I'm saying template on both type name T and type name U, and I'm going to say my return type is auto. Then this add function takes const tref T and const uref U, and then it returns T plus U. Now, you'll notice that this syntax is not valid C++11. C++11 had something very similar where you could say template or just any function. You would say auto the function and then say, here, let me copy this so I don't mess with my test case. Come on, open a new one. There we go. You may be thinking of a similar feature in C++, whatever. return type goes here. In C++ 11, somewhat confusingly, the trailing return type syntax is introduced by auto. In C++ 11, if you put auto for return type, it's saying, hey, compiler, hold on, I'm going to give you a return type, but it's going to appear after the parameters on the right-hand side. And then the return type would be placed there after an arrow. In C++ 14, if you have auto by itself, without that trailing return type, this is the new C++ 14 feature of automatically deduced return types. So what happens here is that the return type of add will be as if you had just declared a local variable and you said auto v equals t plus u. The exact same type deduction rules that are used for local variables would be used for the return type here. So here I've got test1. My function template add, I can invoke it with a couple of integers. T and u would be deduced to be int, and then the type of t plus u would be int, and so add would return int. I didn't have to say it because the compiler already knows, given the input types t and u, what the result of adding them will be. So this will print out 33. However, if my input types are a std string, here I'm explicitly constructing a temporary just to get that std string type, and the other one is a string literal, then the compiler in here knows that the result of adding a std string to an array of constchar is another std string. So the type of auto, or the return type of add, will be returning a std string by value. This is what I want. So this will print meow per without any spaces. So if we look at what my program printed, indeed I get 33 and then meow per. So this is nice. Not only does it allow you to write more terse code, you don't have to repeat types that the compiler already knows, it allows you to write more generic code. Here you don't have to say something like, oh, give me a trailing return type, and then this thing returns the decltype of t plus u, and then add in some decaying. We are able to write such logic in C++ 11, but in C++ 14 it's a lot easier. Now, you'll notice down here, I've got a slightly different example. So if you think back to C++ 11, I know it's so old, that was like 2 years ago. Auto follows different rules than decltype. Let me actually scribble this. Another one here. OK, so if I have something like a vector of int v, okay, fill it with stuff. Here, I'll say, v pushback. Okay. If I say something like auto x equals v of 0, or v front or whatever, the rules for auto, we could go through what it says in the standard, but essentially references and then CV qualifiers are stripped from the return type. So what v of 0 returns is an int ref. This makes sense because I want to be able to say things like v of 0 equals 456 to assign through that reference. What auto does by stripping references and then CV qualifiers is the type of x is a plain old int. I get a copy. Sometimes I want this. Sometimes I don't. So if instead I ask decltype of v0, and then I would say y equals v of 0, something like this. The rules for decltype preserve references and CV qualifiers. They do other extra things. Scott Myers has talks about all of the rules are decltype. They're not that hard, but I read the standard for a living, so maybe they are that hard. In any event, what decltype of v0 is, this thing will be int ref. It is the declared type of this expression. So here I'll get an int ref bound to the int inside the vector. This is not an independent copy. And if I assign to y, I'll be assigning to the int inside the vector. So with the C++ 14 auto return type, because this follows the rules for plain old auto, where it strips references and CV qualifiers, what if you don't want that? Well, they also added decltype auto return types. This is a combination that was not valid in C++ 11, but in C++ 14. If you say decltype of auto, this says use the decltype type deduction rules. I know it may seem very complicated, but if you program templates for a living, this sort of thing is awesome. It makes your life so much simpler. So here, I'm writing a simple template function, template type name C for some container, and I'm going to call it zeroth. It's going to do something really stupid. It's going to take a container by reference, and it's going to index and get the zeroth element of that container. Now, if I said plain auto, it would return a copy of that element because the reference would be stripped. If I say decltype auto, it will preserve any references. So in my test2 function, if I have a vector in v initialized to 100, 200, 300, I can call zeroth of v. This will invoke v of 0 and then return an int ref. I can increment that, or I could assign to it, or I could just read from it. Here I'll increment, and then I'll print it out. I'll print it out by directly accessing v. So this should prove that if this increment directly modifies the element, I should get 101. And indeed, if I look at my program, I get 101. So sometimes you're going to want auto for your return type. Sometimes you're going to want decltype auto. If you start using these deduced return types, you need to be aware of the difference. Sometimes you want one, sometimes you want the other. In fact, this a mistake confusing the two snuck into the C++ 14 working paper before it was fixed. It was in the apply example. So that's auto and decltype auto. More fun with lambdas. So C++ 14 added a feature that many people were waiting desperately for called generic lambdas. So in C++ 11, lambda expressions allow you to conveniently define and construct little function objects, potentially capturing data members by value or by reference. But they had one major limitation, and that's that they were what is referred to as monomorphic. C++ 11 lambdas have a fixed signature. So you can make them take whatever you want. You would have to specify the types at the point of defining the lambda. Sometimes this is really obnoxious. For example, let me bring up an editor. Imagine that I've got a vector of stuff, or string, or whatever v. I fill it with stuff, and then I want to sort it, but according to a custom comparison. Actually, let me just make this string. Imagine that I wanted to sort v begin, v end, according to my lambda, which can be stateless. Here I would need to specify the types because the lambda can only have a fixed signature. I would have to say constring ref L, constring ref R, and then do something like return L size, blah, blah. So this is the best that I could do in C++ 11. If I wanted to sort types that are even more verbose, I would have to repeat the types here. This is actually kind of obnoxious because ultimately the compiler knows the element types. The thing is, it knows them at the point of invocation of the function object. At this point where I'm defining the function object, this element type is completely disconnected. So that's why C++ 11 required you to specify it separately. In C++ 14, you can now define what are known as generic lambdas. Here is an example. So here, this is a simple generic lambda that is going to add two things. I define the lambda. Again, I introduce it with empty square brackets saying, here's a stateless lambda. And now, again, the committee loves using auto for automatically deduced things and hates introducing new keywords. I declare my lambda as taking const auto ref x, const auto ref y. And then I can just return x plus y and get an automatically deduced return type. This lambda then can be invoked on 33 and 44. That should add two ints and give me 77. Yep. And the exact same lambda can be invoked on a string literal and a stood string, and this will return kitty cat, and indeed it does. So what this is stamping out, I've been saying for years, ever since 2010, lambdas don't fundamentally do anything magical, even though they've been granted things like implicit captures and now generic lambdas and automatically deduced return types. But ultimately, what the compiler is doing is taking your lambda expression and it's stamping out a function object class. when you say, actually, I'll write in my editor. When I say a lambda like this, let me show you the transformation that's happening. Conceptually, what is happening is I'm getting a struct lambda that the compiler is going to generate. It's going to have some internal horrible name. And this is going to now have a templated member function call operator. So it would look like template, type name x, type name y, and then it would actually have an auto return type. I can write this now in C++11, or C++14, sorry. Operator paren taking const x ref x, const y ref y. Implicitly it is const. And then it will return x plus y, which is the body there. And there's my end, and my braces are completely mangled, but there we go. So when you say auto in a C++14 generic lambda, what you're getting is a templated function call operator on that lambda, and you get a unique template parameter for each occurrence of auto. This is important. Even though I said auto twice here, I'm going to get a different x. I'm going to get one template parameter for the first occurrence of auto and another template parameter for the second occurrence. So that's why I can add things of different types. Like here I've got an array of 6 const chars, and here I've got a std string. This is possible because each auto is separate. If for some reason I wanted to require them to be the same, I could then write a handwritten functor templated on a single type name. But in fact, most of the time you actually do want to permit them to be different. It turns out that if you say const tref, then having things like this fail to compile is actually kind of annoying. It's better to permit the types to be different. By the way, because you can take things by auto ref, you may be wondering how to perfectly forward. So if I have a lambda here, imagine I've got some function inner that I need to invoke, and I want to write a generic lambda to perfectly forward. I can do that in C++14, but the syntax may seem a little strange. So I would write my lambda, and I would say auto ref t, and then I'm going to call my inner function. So usually I would say std forward of t, like this. The problem, though, in a generic lambda is that I don't have a type capital T to refer to. If I try to say something like auto here, this will totally fail to compile. You can't write this. What you have to write may look a little strange, but it totally works. You say this. Turns out if you work through the rules of decltype, saying std forward decltype of the variable and then the variable itself, this does the right thing and perfectly forwards t. In the future, the C++ Standardization Committee may introduce dedicated syntax to make this less repetitive, but for the time being, this is the best we can do in C++14. There is always room for the language to evolve and improve. OK, so that is generic lambdas. By the way, there is a caveat. I've been writing in red here, notes to myself. Because this is a very early alpha of the compiler, I mean, it's literally coming fresh out of the build lab. Some things are not implemented yet. Many of these deficiencies will be corrected by the time we reach RTM of the next major version. But in the case of generic lambdas, there's a limitation that will persist even until the next major version, and that's generic lambdas require explicit captures. So here in my editor, I can write a generic lambda that is stateless. If I have empty square brackets, totally fine. This is OK. If I have explicit captures, like I say, I want to capture x by value, and by the way, I want to capture y by reference, and then it's going to be generic, this is totally cool as well. However, if I try to implicitly capture things by reference and then make a generic lambda, C++14 says this is totally valid. But it will be an error in CTP. Similarly, and I believe, although I haven't checked, that you'll actually get a dedicated error saying, hey, this is not yet implemented. Similarly, if you ask for explicit value captures by, or sorry, implicit captures by value, again, it's going to be an error in CTP. And this is true even if you add in some explicit captures afterwards. The reason why was explained to me by Jonathan Caves, our compiler dev. Turns out that asking for implicit captures when the member function is going to be templated, this is quite difficult for our compiler to do right now. They're working out ways to make this work in the future, but they don't believe that they're going to have it ready for the next major version. So don't be surprised if you try to do that and it does not work. Additionally, and I was confused when they told me about all of the features here, there is a separate innovation that C++14 has granted to lambdas. This is not implemented in the CTP. It is a separate feature. They're looking at it, but it's not yet available in the CTP. They're called generalized lambda captures, and actually I've got the standards up for it. In C++14, you can say things like, OK, I'm going to make a lambda, and I'm going to give it a capture called x, and it is going to be a separate integer. Actually, here the standard has chosen a really confusing name. The lambda is going to get its own copy of x, and it's going to be initialized from this outer x plus 1. Or I could write a lambda that would look like something like y equals some outer x plus 1. These are what are known as C++14 generalized lambda captures, where you can put arbitrary initializers. That's a separate lambda feature. It's really cool, but they did not have time to implement it for the CTP. And we're not promising it for RTM either, but they are looking at it. OK, so that was generic lambdas. OK, next on the list, unconditional noexcept. So in C++9803, there were these things called dynamic exception specifications. They would look like, in my editor, void meow. I could say something like throw pren pren. Or I could say, you know, throw bad alc. Or things like this. These are what are now known as dynamic exception specifications. And they're deprecated in C++1114. Turns out the committee is making a frowny face at them because they are not nearly as useful as people thought back when they were first standardized back in '98. The standard says that dynamic exception specifications need to be enforced at runtime, not at compile time, with a call to stood unexpected. And by default, this calls stood terminate, which by default calls stood abort, which brings down your whole process. Unexpected can do some other fancy things like translating an exception and throwing something that is permitted, blah, blah, blah. The rules are complicated. VC does not implement, and still does not implement, dynamic exception specifications. So if you try to say throw bad alc, you'll actually get a warning saying, hey, we don't implement this thing. It is technically a conformance defect, although it's deprecated, and I would not hold my breath waiting for this to be implemented in VC. There's one thing the VC does implement, but it's with non-standard semantics. If you say throw pren pren, what VC does is it considers this non-conformantly identical to a declspec no throw. And what this means is assume that this thing will not emit an exception and optimize accordingly. So that's cool because it optimizes. If you then actually emit an exception from something that is either marked declspec no throw or in VC has been marked as throw pren pren, you'll get potential corruption. The compiler is optimized based on information. That is not true. It thought you weren't going to throw an exception, and you did. And you can totally corrupt your program. I've seen people actually report bugs to me where they had marked a function throw pren pren, and then they threw an exception through it, and it caused corruption later in their program. So VC's behavior has not changed in the CTP, but we have implemented C++14's noexcept. So noexcept takes this sort of squirrely behavior of calling unexpected and instead replaces it with something else. So actually, let me show you my function here. Actually, did I say C++14? In C++11, you can say noexcept. So here I've got a function, it's very simple, called get1. It takes a map by const reference, and it calls .at. This is a member function, the map, which can work on const maps, and will look up the key here 1, and then return the value, and here I'm going to return a constring ref. The noexcept feature allows you to mark a function as noexcept. What this says is several things. First, the function is not allowed to emit an exception. It can throw internally, but it needs to catch it. So the function in here could have a try and a catch, and everything would be fine. If it actually does emit an exception, what noexcept requires is a guaranteed call to std terminate, which will bring down the process. You can customize the terminate handler, but you can't do anything like throw another exception from it. The process is going to terminate. So here, if I construct a map and then fill it with a bunch of things, and then I call get1, if this succeeds, then I return a string normally. And in fact, the compiler will optimize based on noexcept. If you look at the standard, actually let me open this. If we look at things like the specification of std vector, we will see that a whole bunch of things are now being marked as noexcept. For example, begin and end on a vector. These cannot throw an exception ever. So the standard now requires them to be marked as noexcept. By the way, this is one of the things we will be looking at implementing in our standard library, but because the CTP is a compiler-only CTP, the STL does not yet say noexcept anywhere. Instead, we're doing something else. The compiler can optimize accordingly when you say noexcept, and yet you get guaranteed runtime validation if that's violated. So here, I've guarded this with an if-def. If I define program go boom, and my map does not contain the value I'm looking for, then map at is required to throw an exception. I believe it's stood out of range, although I won't absolutely swear to that. And if I try to throw an exception through noexcept, I'm going to get guaranteed termination. So let me show you what this should do. So here, if everything works in my first map, I'll look up value 1 and I print that out, and that's TNG here. Awesome. But what if I define program go boom? Here's what C++11 requires. / define program go boom. Compile, run, and there we go. I get my guaranteed call to terminate, which then invokes std abort, and then I get this nice little dialog saying, we have aborted your program. There we go. Now, there's a caveat. This works for me because I'm using a local build of the compiler and the CTP, and the CRT. However, in the Visual C++ compiler November 2013 CTP, they're shipping this without a modified CRT. And yet, to invoke this guaranteed std terminate, it needs CRT support. So in the CTP, you will not get the guaranteed terminate behavior. You'll see this in the next RTM when we can actually modify the CRT, but you will not see the std terminate part. The other parts will work. You can put noexcept on your functions, and the compiler will optimize accordingly. But if you try to actually throw through a noexcept, you're going to get the throw pren behavior that VC has, where it optimizes based on it, and it corrupts your program because you threw through it anyways. Now, when I say unconditional noexcept, this means that we have not yet implemented something else. In C++11, the noexcept keyword can also be used conditionally. You can say, this function is marked noexcept if and only if some other expression can be known not to throw an exception. The standard does this in a couple places for like swaps and I believe a couple move constructors. That requires more compiler machinery, which they're looking at, but it's not in the CTP, and we cannot promise it for RTM either. OK, next feature. So constexpr. This is one of the few times where the committee actually decided to add a new keyword. I guess noexcept was another one. In C++11, if you mark things as constexpr, you're saying this is a constant expression, and I would like to be able to use it in places where a constant expression is permitted. In C++11, the feature was rather restricted. In C++14, it has been enhanced. You can make all sorts of things constexpr now, including like for loops. I sort of feel sorry for the compiler devs who have to implement this really complicated stuff. It turns out that constexpr is one of the most complicated features to implement in C++11 and 14. We have part of it implemented in the CTP. So here, I have a function template templated on TNU. I'm going to use the automatically deduced return types because why not? I'm going to take const_tref and const_uref, and I'm going to multiply them and return them. I then mark this as constexpr. So what does this allow me to do? Here I've got a function I can then use my molt function in places where a constant expression is required. For example, I can give molt23 or molt57 to the template stood ratio, which is templated on a couple of integers. This is a function call. In C++ 9803, this would be totally forbidden because you can't give a function call at runtime to a template at compile time. But with the magic of constexpr, this works in C++ 11 and 14. So here I can static assert that a ratio of 2 times 3 over 5 times 7 should be the same as the ratio of 6 over 35. And so merely by compiling, let me get rid of my program go boom, this proves that constexpr is generating something that can then be given to a template. Now there is a very important restriction here. Because constexpr is such a large feature, they've only implemented part of it for the CTP. This first part consists of constexpr except on non-static member functions. So here I can apply constexpr to an ordinary function that is not a member of a class that's working on what turn out to be integers. But putting constexpr on member functions of a class that's allowed by C++ 11 and 14, it's not yet implemented in the CTP. So all of that stuff, including what are known as literal types, that's not yet implemented. They're looking at that for RTM, but it's a large feature. We can't promise that it'll make it. OK, so that's constexpr. Next up, more things with R-value references. As you may be familiar with, we can take member functions. For example, stood vector has something that looks like operator bracket bracket taking a size t index. So if I'm calling operator bracket bracket on a modifiable vector, I would like to be able to say things like v of 0 equals 1, 2, 3, or whatever. So operator bracket bracket really should return a modifiable tref. However, imagine that I have something like a const vector int, let me get rid of this, v, and then initialize it with stuff, 11 copies of 1729. I would also like to be able to say, hey, let me go read v of 0. But I obviously don't want to be able to modify things inside my vector. So I would also like vectors operator bracket bracket to return const tref. In C++ 9803, this is achieved through CV qualifiers on member functions. So I can have this because the member function, this is a member function of vector, is marked as const. And I can actually overload based on this. So what this says is that this operator pren will be invoked on objects that are modifiable. Operator bracket bracket. This operator bracket bracket will be invoked on objects that are const. It's essentially overloading on the this pointer. Now in C++ 9803, we can overload on the constness of an object, but we can't detect whether the object is an L value or an R value. In C++ 11, we gained R value references, which allow us to detect whether input parameters are L values and R values, and that enables all the cool stuff like move semantics and perfect forwarding. However, what about yourself? What about the this object? They added in C++ 11 a feature known as ref qualifiers that allow member functions to sense whether they're being invoked on L values or R values. Without this, it would be very strange. You would be able to sense the L valueness and R valueness, or value category, of everything except for yourself. That's kind of weird. Ref qualifiers complete that, and they fill this hole. So here, I can have a struct x, and this is a very simple example. I've got void f taking nothing. One is marked for L values, and one is marked for R values, and they print out things accordingly. So if I have a named object x, and I invoke the function on it, I should see I'm an L value. But if I have a temporary x and I invoke f on it, I should see I'm an R value. And indeed, this is what I get. I'm an L value for the named one. I'm an R value for the temporary. This is rather simple. I cannot actually think of a reason why you'd want to do this specific thing. However, it can be very useful in general. You can actually, no, stood optional head, then that was removed. Sometimes you want to declare, actually let me open my editor. Sometimes you want to declare a function as not being available for things that are R values. So if I've got something like a struct a, and I had something like a void f, I'd say, okay, go do cool things. But if I'm invoked on a temporary void f, for some reason this would be bad. For example, I'm going to return a pointer to my internal data, and if I'm a temporary, I'm going to evaporate at the semicolon, and that would be bad. So I want to prevent this from compiling. So in C++ 11, I can say, okay, f for r values, I'm going to delete this. I can combine these features and say, for L values of type A, do this thing. For R values, fail to compile. This is why ref qualifiers are useful. It's definitely a minor feature. It's not useful all the time, but when you want it, it is there for you to use, and it's available in the CTP. Next up, another feature, inheriting constructors. So in 2013 RTM, there's this feature called delegating constructors, where you can have constructors and an object invoke each other. And this is very useful to centralize things. But what if you are derived from a base class and you'd like to say, hey, I would like all the same constructors as that base class? That's what this separate feature called inheriting constructors is for. And this is provided in the CTP. So here I've got a base class B, and I'm going to say, okay, B is not default constructible, so I'm deleting it. B is constructible from constchar star, and I'm going to print out, okay, I'm constructing B from constchar star. And B is constructed from 2 ints, and I'm going to print that out too. So in C++ 11, you can say, I have a derived class, or in this case a struct, derived from B, and I can say, okay, I want all the same constructors as B has, but for my derived object. The syntax for that is using base ;; base. So if I say this, D then gains a constructor D, taking a constchar star, and it's going to give that constchar star to its base constructor. And similarly, it's going to gain a constructor taking 2 ints and passing that up. So if I construct D1 from meow, I should expect to see that, okay, D has been constructed, it does nothing, but it calls the base constructor with a constchar star. And similarly, D2 will print out that the base constructor from 2 ints have been called. And that's what I get here. So I can inherit the constructors of a base class. This is occasionally useful, and now it's available in the CTP. Okay, next. Sometimes you would like to be able to query the alignment of objects and classes, and then say, okay, I want to align this array of characters or whatever to 8 bytes or 16 bytes or whatever. We've had for quite some time the standard library machinery known as aligned storage and aligned union. In 2013 RTM, we fixed aligned union to actually work. It was doing something incorrect before. But there are also core language features to deal with alignment, and these have been implemented in the CTP. So here I've got very simple examples. Remember that noisy instruct, which was up here? It had an empty noisy data member. It had an int and an unsigned long long. Unsigned long long is 64-bit, that's 8 bytes. The alignment of noisy int containing an unsigned long long should also be 8. So I can now ask in C++ 11, give me the alignment of noisy int. This is a core language feature, just like I can say size of noisy int. They actually added a new keyword for this. I was surprised. So if I ask for the line of noisy int, I get 8 printed. Well, that's nice. I can also say, okay, I've got an array of bytes, unsigned char. It's going to be as large as noisy int, but I also want it to be properly aligned. The core language allows you to say, align this array with the same alignment as noisy int the type. I believe that you can also put an integer in here. That should work. I haven't tested that personally. So here I can construct an array of bytes and have it put by the compiler with an 8-byte alignment. We previously had a declspec align that was non-standard. This is the standard functionality for this. I could also spell this with the type traits header with align storage or align union, but if you want the core language, this is now supported. A couple other minor features, extended sizeof. Turns out, in going all the way back to C, but in C++ 9803, if I have like a struct, and I want to get the size of one of its data members, and I don't have an object of that struct handy, I couldn't say size of noisy int double colon I. This was forbidden. This restriction was kind of silly, and they noticed it, and in C++11 they fixed it. So you can now ask for the size of a struct double colon data member and have that work even without an object of that type available. So in this case, I've got noisy int, and my I is an int, so the size of that should be 4, and indeed it is 4. Awesome. And you can also ask in C++11 for the name of the function you're within. This is done through double underscore func double underscore. Despite the double underscores, this is a standard feature. It's just like if you have double underscore file or double underscore line, same sort of thing. Double underscore func gives you the name of the function you're in. In this case, I printed this out from test 6, and my program does print test 6. Awesome. We have a couple non-standard macros for this. It's like funcsig. They're documented on MSDN, but this is the standard functionality to get the name of the function you're in. Finally, a couple features, or one feature I do not have an example for, magic statics. This is the feature that was proposed, and its title is Dynamic Initialization and Destruction with Concurrency. I thought that was a mouthful, so I came up with the term for it, magic statics. What this means is that if I have a function, something like void foo, and I have a static int I is, whatever, func, or I could have like a static string, s is other func. What would happen if I had multiple threads simultaneously calling foo? Well, C++9803 did not recognize the existence of threads. And VC, accordingly, did not protect this in any way. So if you had multiple threads calling foo, trying to simultaneously initialize I or S, you would get a data race and potentially crash. That would not be good. In C++11, this is now required to be thread safe. So you can have multiple threads simultaneously calling foo, and it is guaranteed that I and S here will be initialized exactly once. And there's rules for what happens if an exception is thrown, blah, blah, blah. And it's required to be thread safe. The proposal came with an algorithm, a novel algorithm specified by Mike Burrows that can do this very efficiently. And we have implemented this in the CTP. I haven't depicted it because it would just work. And it would not crash if I had multiple threads trying to invoke this. I guess I could look at the generated assembler. There's one caveat, though. In the CTP, this does not work under /CLR. When we're generating managed code, the concurrency runtime is not compatible with that, and this is powered by the concurrency runtime. So it's not thread safe under CLR, but it is planned to work in the next major version, the next RTM. Finally, the CTP contains an extension. This is not part of C++14, but it is a proposal. I have a snippet that our compiler dev, Dion Brewer, sent to me. This is called await. It's part of the resumable functions proposal. When you're writing concurrent code, if you want to read in a file by chunks, the code to do that looks actually quite nasty. Here's the example that he sent to me. When you're chaining lambdas, or when you're chaining futures or tasks with .then, the code for it is quite complicated. But you can then say, with this await extension, this is a resumable function, and I would want to try to read from this file stream, and when it's available, start this or resume this lambda, and the next time I block, go put it off onto the side. Herb has presentations about this. Every time I view his presentation, I understand the feature. And then when he's done, the feature instantly goes out of my brain. I expect someday I will understand this enough to be able to talk about what it's doing. So this is implemented in the CTP, but because it's an extension, we have implemented it with the double underscore await and double underscore resumable. We know it's not standard. That's why there's the double underscore. We hope that it'll make its way into a future version of the C++ standard, but until then, we've got these double underscores. So that's all the features that are in the CTP. We will have a download link for you. We will also have MSD and documentation at some point. I don't know if it will be simultaneous with the CTP's release. If you have any questions, ask me in the comment, and I'll either try to answer them myself or get a compiler dev to answer them for you. See you next time.